In our last lecture, we saw a brilliant application of Einstein's dictum that imagination is more important than knowledge. It occurred with Stephen Hawking, who, having run out of all of the mathematics that we physicists use to understand the world, inserted his imagination to try to get to the next stage. I have going on the screen here an illustration of this, of sorts. This will loop around so we can watch it. In the phase of before Stephen Hawking, we thought that if you looked up on a starry night and a black hole happened to pass through your field of vision, what you would see would be the stars being distorted in their locations as you see here. And we thought that this was the only thing that the black hole would do. In 1919, there was an expedition to two places, Brazil and to a set of islands off the coast of Africa. These expeditions were led by an astronomer named Arthur Eddington. And the results for which these expeditions were put together was to try to find out if Einstein was right. Remember, in 1916, he had predicted that gravity can bend light. And in our graphic, we're using that effect here to talk about the distortion of starlight. But in 1919, no one had ever seen gravity bend light. So this English pacifist, who had almost been thrown into jail during the First World War because he was a pacifist, found himself leading two groups to check to see whether Einstein had gotten it right. One group went to Brazil, and as I said, the others were in islands off the west coast of Africa. It turns out that these expeditions both faced some challenges, but interestingly enough, it was the expedition to the west coast of Africa that got the data that proved to us that gravity bends light. That's what we're using here. After Stephen Hawking, we came to understand that black holes do more than just bend light around them. They give a kind of sizzle. They have a kind of static that they give off. In my graphic, as the black hole moves from right to left, from my perspective, what we see is it bends light, and then we see a spray of particles. This spray is to represent the heat that a black hole is capable of giving off. So that was the genius of Stephen Hawking. In order to reach that, one has to combine two of the pillars of physics. One of them is quantum theory, and the other is the theory of general relativity. We had talked in a previous lecture also about general relativity. Here we have an animation of the Earth going around the sun. As you can see, there are these indentations, and I repeat that these lines are not things that you're actually going to see. These are illustrations of the mathematics of space-time as the Earth goes around the sun. So as you see in this graphic, there's an indentation around the sun. That's a representation of its gravitational field. As you look at the Earth, you'll see we have indentations both above and below. Those are representations of its gravitational field. There is a mathematical function that describes these indentations. It's the thing that is called the metric. It's the object that Riemann had used simply to talk about how geometry changes when you try to do geometry on a plane versus how geometry acts on a sphere. So it's that same mathematical object that we're looking for pictures to represent when we see such diagrams. So we've got metrics. We have a way to understand, at least using Stephen Hawking's imagination, how black holes can be consistent with the laws of thermodynamics, but what we're lacking is good science. You see, science doesn't work by someone writing a paper using mathematics at one part, and then at a sudden point waking up and saying, gee, I want to use my imagination, so I'm going to plop down something in the paper and I'll call it science. That's not good science. And yet, that was the only thing that we could do at the end of the 60s to try to understand black hole physics. We also had to confront the fact that quantum theory and general relativity do not work well together. So, in order to move beyond this point of view that it's the best that we can do to insert our intuition, a new idea had to come from somewhere. Now, science, when you read it in a book, sounds like a novel. First, person A does something, then person B follows up with something different, and then person C follows up, and it all sounds nice and scripted. But of course, that's not the way the real world works. In the real world, it's more like a billiards game where one idea bounces off the side of the table and then careens back in a different direction, and then a ball that someone had over here, which you had no idea was important, suddenly comes into play. And the history of string theory sort of is a great illustration of this point, because when you look at Stephen Hawking's problem in the 60s, it's totally removed from a different set of problems. What other problems? Well, in these lectures, we've talked about hadrons and how the fact that a proton is sort of like a bubble that has small bits of matter inside of it called quarks. About the time that Stephen Hawking was worried about the heat coming off of black holes, there were other physicists trying to understand the structure of hadronic matter. And in these there were experiments that were conducted to understand hadronic matter. Some of these experiments had a very curious result. And there's an analogy that one sometimes hears about what's going on. And it goes as follows. Suppose you wanted to figure out how to make a watch. Probably the last thing that you would do would be to take collections of watches and bang them together as hard as you could, watching the pieces fly out, and then from that deduce how the watch is put together. In some sense, that's what we do in particle physics and nuclear physics. That's why devices like the Large Hadron Collider or the Stanford Linear Accelerator are necessary. They allow us to collide matter in extreme circumstances, and then by observing the products of those collisions, deduce something about how matter works. So, back at the end of the 60s, when people were trying to figure out how protons work, there were many collider experiments. And a curious result from these experiments was that oftentimes when you would collide nuclear matter and then look to see what remnants come out, you would find objects that bear a striking resemblance to the inputs. And when you made plots of these objects, you could draw them on straight lines. There would be the initial object, and then another object that had properties very similar, and then a third object that had properties similar to the first two, and so forth, all along a straight line where in one direction you plot energy, and in the other direction you plot spin. Remember, we talked about the fact that small objects spin. These straight lines were called Regge trajectories. And when physicists observe them, then the problem becomes, why are they there? At this point, string theory actually first was born. Gabriele Veneziano, on observing these straight lines, looked for a piece of mathematics that would explain why they were there. And he found it. There's something called the beta function, which is mathematics that comes to us from the 18th century. And Veneziano, by applying this mathematics, found he could explain these wonderfully straight lines that we saw in the experiments. Now, that was progress, but it wasn't enough, because if you have this mathematics as a scientist, remember, for physicists, mathematics has to have a picture attached to it, the thing we call the model. So, why was the beta function appearing? It was realized by Lenny Susskind, among other physicists, that you could understand the beta function if you were looking at objects that look like strings. That, in fact, is where string theory had its birth, not in thinking about gravity at all, but in trying to understand how nuclear physics works. Now, this idea and this description of nuclear physics doesn't rely on quarks. In fact, quarks and strings were what we call competing models in physics. In other words, one is a possible explanation, but the other is an entirely different possible explanation. The way we scientists decide on which is correct is that we do experiments. The deep inelastic scattering experiments settled the issue. Quarks were right when you want to talk about nuclear matter. But this curious mathematics of string theory didn't go away. Just because that mathematics didn't describe nuclear physics doesn't mean that it was wrong. In fact, there was nothing wrong with the mathematics. We were trying to apply it in a place where it was not applicable. Now, string theory diverges from several hundred years of physics because in string theory, our most fundamental objects are tiny filaments that we first saw in lecture number 1. All of the rest of classical physics is based on the notion that if you want to understand everything in our universe, start with a game of billiards. Why a game of billiards, you would ask? Well, if you actually film a game of billiards, you'll see balls bouncing off of each other and careening across the table. And if you try to write the mathematics that describe that motion, you get led to Newton's second law. Newton's second law is a mathematical description of motion. So implicit in these equations is that there are things in our universe that behave like little balls. In fact, all of our physics has been based on this idea. We physicists call these things geometrical point particles. A geometrical point particle is, well, start with a ball that has a mass, let the ball shrink just as we were letting the Earth shrink in our previous lecture, and keep all the mass there. When you get to something that has no size whatsoever, you've reached the geometrical point particle. Perhaps you remember in elementary school this thing called the number line, because that's the first place many of us meet this notion. Teachers tell you numbers correspond to points on a line. The points they're talking about are geometrical points. So all of Newton's laws are based on this view that balls are a good place to start. Now you might say, well, quantum theory changed that. Well, yes and no, it did and it didn't, because although we started replacing balls by waves, mathematically the way you describe these waves actually depends on point particles, because you have to know where an object is located. So you don't totally get away from the little balls even in quantum theory. Well, you might say, well, wait a minute, what about special relativity? Doesn't it work in a different way? The answer turns out to be no. Special relativity simply tells us that when you study these balls, you have to study them in a world that doesn't just have 3 directions. In our world, we have length, breadth, and thickness. But what Einstein did with special relativity is says, no, you must study the motion in a world where there's length, breadth, and thickness, and in addition, duration or time. You go to a 4-dimensional world, but the little balls are still there. So the balls were every place in physics. So string theory is the first time that we try to think about building physics not based on little balls, but, as I said, little pieces of pasta. Now, we've seen in previous lectures some representations of these objects. So here's a closed string. And as you can see, we've drawn essentially a little filament. And this filament is capable of moving. As you can see, it's moving back and forth on our screen. But while it's moving, it is capable of producing incredibly complicated modes of vibration. And this is a property that no tiny ball can replicate. So the notion of the string has been described by, for example, John Schwartz, a physicist that we will meet in a future lecture, as a radical conservative reformulation of physics. It's conservative because it uses all of the ideas that were applied to little balls, but it applies these ideas not to little balls, but to little pieces of pasta in some sense. So this is the beginning of string theory. Now, whenever in physics one proposes something new, it is incumbent to find out if it agrees with what we knew before. Because you see, in science, accepted theories don't really get thrown away. What we find is a range over which the accepted theory works, and then outside of that range, we have to go to something else. So, for example, Newton's laws work that way. We're very comfortable with the notion that were I to toss a ball up in the air, it would follow this nice, beautiful arcing path, the thing that Newton's equations calculate, and that's an accurate description of nature. We don't worry about what the electrons are doing in the ball, because that's not really what we're after. We want to know what the ball is doing. So Newton's laws, at some level, work. But when you try to talk about the motion of electrons, you have to change your point of view. And that's why we go to quantum theory. So accepted theories are never really thrown away in science. We come to the limit over which they are applicable, and then we create a larger theory that has to work outside of that range more accurately. Also, it must be true that this larger theory is capable of connecting to the predictions of its previous predecessor. So in string theory, since you now have switched from little balls to little pieces of pasta, the first thing you have to do is check, does it agree with what was there before? Well, we know that in our universe, according to the laws of special relativity, nothing can travel faster than the speed of light. That was one of the great discoveries of 1905 with Albert Einstein. Nothing can travel faster than the speed of light, according to our understanding of the universe. The speed of light in a vacuum is about 671 million miles per hour. That's almost unimaginable. The universe is about 14 billion years old. So imagine there was a light beam that had been traveling for 1 trillion, not years, but times the age of the universe. The distance covered over this period is practically unimaginable, especially compared to your height. But if you take your height and divide by this number, you get something that's incredibly small. That number, that length, is about the size of a string. It's called the Planck length. The actual value of the Planck length is found by taking h bar, that's that spin rate we talked about, multiply that times g, Newton's constant for gravity, and divide that by the cube of the speed of light. This is incredibly tiny. Do they obey the laws of special relativity? We've described them as being filaments. They're like strings on a violin. They're like pasta. However, since they're far smaller than the molecules of air that we have around us, if they vibrate, they cannot actually produce notes. They're too small. So we have to understand what are the vibrations that these strings produce. If the idea of string theory is correct, strings ultimately are the DNA of our reality. They are the ultimate mathematical description of the laws of nature as we've been able to understand them. One of the things about string theory that's interesting is it's intrinsically quantum mechanical. When we were talking about the little balls, we could apply the laws of Newton, in which case we call that classical Newtonian physics, or we could apply the laws of Schrodinger and Heisenberg, in which case we would replace the balls by waves, but the location of these waves would depend on the balls. So that's how it fits together. When we use the laws of quantum mechanics, the world inherits a kind of weirdness. One of the things that it inherits is what we call zero-point energy. Let me talk about zero-point energy for a second because it will be relevant to strings. Were I to have a pendulum in front of me, a pendulum from a simple clock, it could swing back and forth. Depending on how hard I push the pendulum, it may swing very widely, or if I give it a soft push, of a nice gentle swinging back and forth. And anything in between is possible by depending on how much I push. On the other hand, if I don't push at all, you expect the pendulum to hang vertically with no motion whatsoever. That's a classical description of how pendula, or how what we physicists call harmonic oscillators, behave. In the quantum world, this is not true. It turns out that if you take a quantum pendulum, it can swing at one distance, or it can swing at another distance, but not in between. There are quantized regions of swinging. It can swing a distance of, let's call it A, or maybe it swings to A, but it never swings at 3/2 of A. That's what we mean by quantization. That kind of behavior is what explains the spectrum of atoms. Electrons can orbit at one radius, or they can orbit at a bigger radius, but they can't orbit at a radius in between the two. That's what quantum theory tells us. So the 0-point energy is an intrinsic part of quantum behavior. And since strings are quantum mechanical, they have to have 0-point energy. They cannot get away from it. They have to always move. That's the important message. You can never think about one of these things completely at rest. They have to always have some vibratory motion associated with them. Are they consistent with special relativity? Well, here something very interesting goes on, because if you compare what Einstein talks about applied to particles and compare that to what the equations of string theory tell us, there's kind of a mismatch. And in fact, this mismatch is one of the strangest aspects of string theory that will lead us to a realm which perhaps is shocking. We're going to come back to that, but let me spend some more time on the quantum aspect, because it's very important. The way to think about the quantum aspect of a string is by looking at real strings. If I have a real violin string, I can pluck it and listen to its note. It turns out that if you watch a real object, they fall in very definite sorts of patterns of vibration, and let me show you some of these patterns. In this diagram, we have a pipe. The ends of the pipe are open, and this straight line that you see represents the average velocity of air molecules. So now let's set this into motion and see what happens. You see, this average motion is kind of like a string. And as you can see, this object, as it vibrates, moves back and forth. And in fact, that motion back and forth is what we call sound. Now, what's interesting about the pipe is that we're going to find out that this is very relevant to the string. As I said, this pipe has open ends. Let's look at a pipe where the ends are closed. For the pipe that's in where the ends are closed, you will notice that as it's set to motion, that the endpoints of the object have to stay in the same location. Now, that's not really surprising, because you see, at the end of a closed pipe, the air is not allowed to move outside of the pipe. So that's why its location is fixed. Now, earlier, when I introduced string theory in lecture number 1, we talked about open string versus closed strings. And it turns out that the mathematics of open strings versus closed strings is exactly the same mathematics as open pipes and closed pipes. One of the most interesting things about this is that when you have a closed pipe, it actually has more motions, or what we physicists call normal modes, associated with it. Well, why is that true? Well, in order to get a closed pipe, one can think about having a wave where one piece moves in one direction and the other moves in the other, and that's why the ends stay still, because you have them exactly balanced on the end. So you need at least these two kinds of waves in order to keep the endpoints fixed. On the other hand, for the open pipe, the ends were free to move up and down. And since there was no constraint that says that you have to keep the ends fixed, it means that the number of vibrations that you can support need not be as great. We see exactly this behavior in the mathematics of string theory. In string theory, for the open string, we find that there are less particles associated with it. Now you might say, wait a minute, where'd the particle come from? Since the string is too small to actually produce sound, it produces something when it vibrates. From our perspective, these somethings are particles. In fact, this is the great secret of string theory. Things that to us look like different particles correspond in the string to simply different ways of vibrating. So when a string vibrates in one manner, we might think it's an electron. If it vibrates in a different manner, we would say, gee, that's a quark. It could vibrate in a third manner, and we would say, no, that's a photon. Or perhaps it vibrates in a fourth manner and we say, no, that thing over there is a graviton. So all of the list of denizens that we met when we shrunk to the quantum world, where we thought they were all different from the point of view of string theory, correspond to one object which vibrates in different ways. And so strings have an inherent capability to unify things that we thought were different. Now, open strings versus closed strings have one other attribute. It turns out that when you look at an open string and its vibrations and ask, what are the particles that are associated with that? You'll never find the graviton among them. The only particles that an open string can describe are particles that look, in some sense, like photons or possibly other objects closely related to the photon. But you will never find gravity there. On the other hand, for the closed string, which has more modes in order to keep the ends fixed, what you find is among that mathematics, there is precisely an object that looks like the graviton. In fact, this was the great surprise of string theory. You'll remember in my recitation of string theory history, it started out trying to describe nuclear physics, not trying to describe the whole world. And so it was only later in the history of the subject when two physicists, Joel Scherk and John Schwartz, looked at the mathematics of string theory and noticed that in its mathematics there was exactly an object with the properties of the metric that Einstein had written down. This came as an enormous surprise, and so it was an accident that string theory was born and describes the force of gravity. This accident, of course, was a very fortunate one. So, we get to the point of replacing little balls by extended objects. We understand these extended objects can vibrate just like strings in our world, but they don't produce music. They produce what we think of as elementary particles. We still have yet to face the challenge of whether these obey the laws of special relativity. We will address this in some great detail in the next lecture. But the great message of these things, which we will find in a bit, is that Stephen Hawking's guess about the heat that black holes can generate produce in the equations of string theory the result that he wanted. It's stated another way. String theory is the only consistent mathematics that physicists have developed that allow black holes to radiate heat in precisely the way that Stephen Hawking had to use his intuition to predict. This came as a stunning surprise to the string theory community and to physicists in general, because I'm sure that many of you have heard the criticisms of string theory that it's not connected to any observable or experimental result. And it is also true, unfortunately, that we've never actually seen black holes. We have candidates for black holes in the center of our galaxy. We think, in fact, that most galaxies possess black holes at their center. We also see further candidates for black holes by watching stars that orbit in very peculiar ways. Remember, I told you a black hole has an event horizon, and if you're outside the event horizon, it's not unusual. So you can imagine that there's a star outside of the event horizon of a black hole, and the two of them could simply orbit about each other, exactly as if there were two stars orbiting about each other. We have observed this kind of behavior in a number of stars in the galaxy where we cannot detect, we see one star behaving as if it's orbiting about a second star, but we cannot find the second star. That's some of the strongest evidence that we have that black holes exist, because we think that the missing star is a black hole. And now with string theory, maybe we can begin to talk about the quantum mechanics of black holes.